Get ready to enter a brave new world with your host, Vasant Dar.
Brave New World is supported by the Center for Data Science, or CDS, at NYU. If your organization is interested in engaging with CDS through student projects, please email cdsindustry@nyu.edu. For more color on the podcast and additional commentary, please subscribe to my newsletter at vasantdar.substack.com. Hello, and welcome to Brave New World. I did my PhD thesis in the field of AI over 40 years ago, thanks to my mentors Herbert Simon and Harry Popel. But I never thought I'd see what I'm seeing today in my lifetime. ChatGPT has taken the world by storm. Everyone is talking about it. There's an awe and fear about AI. Has it already gone out of control? There's an old problem in AI called the control problem, which was expressed by the cybernetician Norbert Wiener in 1960, where he said, "If we use to achieve our purposes a mechanical agency with whose operation we cannot efficiently interfere once we have started it, then we had better be quite sure that the purpose put into the machine is the purpose which we really desire and not merely a colorful imitation of it." Sounds prophetic, doesn't it? Joining me today is natural language expert Sam Bowman, who is a professor of data science and linguistics at NYU, currently spending a sabbatical at Anthropic in San Francisco. Sam, welcome to Brave New World. I am delighted to have you on the show.
Thanks so much for having me. Excited to be here.
This is great timing, Sam, to have a natural language processing authority on the show, considering that GPT has captured the world's attention and sparked a whole new level of interest in AI. But before we get into ChatGPT, tell us a little bit about yourself and your very timely entry into this area.
Sure. It's long meandering process. Yeah, I guess I've been interested in this sort of idea of artificial neural networks for a long time. I think probably since at least maybe the beginning of high school. It had just occurred to me, it seems like as far as we know, kind of most of a lot of what we can do sort of comes from these processes in the brain. It seems like we could simulate these in computers. It's not obvious we'll be able to exactly reconstruct a brain, but if we play with things like this, what happens? This feels like this kind of generationally big, important scientific question. So following that passively, I had a passive interest for quite a while. Also early on, this might be getting into too much detail, but also early on was sort of trying to stay a little bit away from big tech. I grew up in San Francisco and sort of came of age during the dot-com bust, so I strongly associated applied tech research with sort of burnout and people working way too hard to not actually successfully do projects and found companies. So I wound up majoring in linguistics. I sort of was trying to avoid setting myself up to go straight into tech, avoid going straight through a CS, and found research opportunities in computational linguistics that were less applied, but it seemed like they were kind of in the neighborhood of neural networks research and felt like there were sort of research areas where I could jump in, do computational work, stuff was happening. This eventually led me to starting a PhD at Stanford in linguistics, not really sure what part of linguistics is going to wind up in, but I was sort of at Stanford around 2011, 2012, and this just happened to be sort of completely the right place, the right time for this interest. A lot of the sort of first work in kind of this generation of neural network models for language had just happened at Montreal and one or two other places. And Stanford was kind of one of the first places to start picking up on this, especially sort of my advisor, Chris Manning, Richard Socher, Andrew Ng, were starting to kind of ask very much the kinds of questions I was hoping someday somebody would ask, and really kind of jumped into that. And I've been trying to dive in and ask this question and see what neural networks can do with language as pretty much my career for the last decade and change.
So what questions were they asking that got you sort of excited?
The very first generation of work was just sort of, can they do almost anything interesting? Can we take some kind of artificial neural network and train it to do any kind of interesting, non-trivial behavior in language? The first couple of tasks that people tried them on and where they started to show some signs of life were sentiment analysis. This is just reading a sentence from a movie review and trying to guess whether that movie review was positive or negative. It's kind of a simple, somewhat toy NLP task, at least in that version. And textual similarity. This is sort of reading two sentences, probably talking about related things, and deciding if their meanings were similar. And people were seeing encouraging results. This was kind of before I got involved. And the question that motivated a lot of my early work, and that was, I think, kind of one of the big live questions at that point, was do they sort of basically understand what sentences mean? Do they have in sort of the most shallow, reasonable sense of the word understand? Are they tracking the syntax of the sentence? Do they know sort of like what words modify what, how the pieces fit together? And are they tracking the semantics in a straightforward way? Sort of when there's a negation, do they know where the negation goes? Are they tracking it properly? Do they understand very simple semantic notions like entailment? Sort of if all dogs are red and Clifford is a dog, then Clifford is red. Can they do that kind of reasoning within text? So yeah, there's less of a sense of kind of do these models know things about the world and are able to do kind of rich, grounded social reasoning or anything like that. It was just this basic question of, do they have the basic building blocks to do anything at all useful with language?
So how was this different from sort of classical linguistics? Because I remember in sort of the earlier days of AI seeing dozens, if not hundreds, of dissertations in natural language processing. There was a prominent NLP researcher, Roger Schank at Yale, who passed away recently, may he rest in peace, who supervised dozens of dissertations in NLP. And I don't know whether it would be unkind of me to say this, but a lot of that stuff seemed to come to not much, that at the end of the day, it didn't seem to work. So what was the turning point that sort of started making things work?
Yeah, so there's sort of two turning points. I think some of the context that had happened before a lot of what I was describing kind of set the stage was what's called the statistical revolution in NLP. And the idea there was to give up, at least temporarily, on this vision of kind of fully writing down, fully manually implementing linguistics and cognitive science. I think a lot of kind of the first generation or generations of NLP, including a lot of Schenk's work, I think was built around this vision that we would figure out how language and reasoning works. We'd write that down and the computer would do it. And there's this, I think, sort of gradual realization throughout the 80s and 90s that there was just too much there, that we could make this work in very limited, targeted settings, but that sort of human reasoning was sort of too heterogeneous and diverse and complex for even 1,000 people for 10 years to be a big enough team to implement it all. And so the statistical revolution kind of shifted toward this orientation of let's learn everything from data. Let's build models that are guided somewhat by our intuitions, but ultimately fill in a lot of the blanks by trying to infer what humans are doing from big, usually labeled data sets. And that was, I think, what got a lot of early NLP off the ground. This is the point where sort of the first machine translation systems start getting meaningfully deployed. But so yeah, I think that idea was historically quite important and sort of reoriented the field around learning. But up to that point, I think the actual tools we had for doing the learning were pretty weak. That there was a lot of interest in linear models and in models where kind of a lot of the work still lived in these feature functions. A lot of the work was still kind of setting up the model very precisely according to your understanding of what it was supposed to be doing, such that like some learning could take place around the edges. And that still sort of hit the same basic problem that just there's a lot of complexity there, and it's more than we could really write down. And so I think the sort of second big shift that this early neural networks work was gesturing towards, and that kind of did play out over the following decade, was toward really fully embracing this learning paradigm, fully embracing this idea that our job as machine learning researchers, computer science researchers, applied computational linguists, was just to figure out how to get the machine to learn, not to tell it anything we already knew, within the hope that it would then pick up all of this complexity and nuance if we gave it just enough data and enough time.
So what was the key breakthrough that started to make this work, this sort of statistical paradigm of learning purely by observation and not giving much in the way of bias or specification to the machine to learn from?
I think the history of the field is interesting because there were maybe a few kind of landmark results at several different points, but I don't think there was ever one landmark idea, or one landmark sort of big discovery. That a lot of the basic ideas around the kind of machine learning that was getting used early on, and even around neural networks, had been around in some form or other since the 50s or 60s. There were no really revolutionary developments that sort of came close in time to this really unfolding in the field. A lot of what was happening, I think, was just this kind of gradual increasing snowballing interest in, oh wait, maybe this will actually work if we sort of lean into it enough. I think if I had to point to the one big precipitating discovery would actually be something that's almost completely outside of NLP and outside of anything that I have any expertise in, which was the idea. I think is usually attributed to a team at I believe sort of Toronto around 2010-ish. Might be getting these details wrong, but the idea of using GPUs to train neural networks. That there was just kind of this observation that these sort of processors that were optimized for graphics, especially graphics for video games, were actually a much more efficient way of training neural networks. That sort of optimizing them to run on GPUs rather than CPUs gave you this sort of pretty dramatic speed up in the pace of learning. And at the point that discovery was made, the neural networks we were able to train were just barely big enough to start to learn anything at all, to start to get off the ground. And so this incidental hardware side, engineering side speed up really, I think, catalyzed a lot of what happened. And also was just genuinely a valid discovery. I think the vast majority of work that's happened since then has used GPUs or chips that are kind of spiritual successors to GPUs.
So was this like stuff going on in vision, where they sort of blew away the competition on the endless data? Is that what you're referring to?
Yes. A lot of that sort of that work around 2010, 2011, 2012 was happening sort of first in computer vision, first on image classification, and then fairly quickly people got interested in, all right, can we apply analogous ideas and some of the same technologies to language tasks?
So that's interesting, because you're pointing to a new sort of way of computing with GPUs as opposed to CPUs. What about on the formulation side of things? That were there sort of more clever formulations that came into the picture that started to make things work? I mean, no, I'm reminded of like an early conversation with our colleague Jan LeCun. I forget when it was. It might have been, I don't know, 2015 or 2016, where he first sort of told me about the word Tvec and sort of this vector representation of words, and that king and queen were similar, and Paris and London are similar, and that you could actually start doing some arithmetic on these things, which I thought was really interesting. Although some people have told me that, this vectorized representation of words was nothing new. It had existed before that. So was there some sort of cleverness in the formulation that sort of set things going as well?
Yeah. I think once again, it's this weird story where the trend has been towards less and less cleverness, more and more toward kind of do the simple thing, do the thing that had been kind of that somebody wrote down 20 or 30 or 40 years ago, and just do it a lot and get the engineering right. So we're Tvec and Glove around 2013, 2014 were, I think, two demonstrations of ideas that some cleverness in the details, but were largely familiar, of how you could train a model to come up with semantically interesting 3-dimensional vector representations for word meaning. Again, yeah, the idea had been around for a while, but it just turned out that um, if you throw kind of billions of words of training data at these things and optimize them well enough that you can afford to do that, you get interesting stuff out the other end. There were a few developments throughout the kind of 2010s that there were kind of changes in the field in how people design systems, design neural network models. But I think a lot of these involved throwing away assumptions that we thought we had to make. One of the biggest ones, one of the most sort of famous ones here, was this transition from recurrent neural networks to transformers. So recurrent neural networks, fairly old idea, sort of 20 or 30-year-old idea by this point, that if you're going to read a string of text, read a paragraph, read a document, you should kind of read it word by word from left to right. And kind of there's this process through time where kind of first the model reads the first word, then it reads the second word, and it's gradually updating its understanding as it goes. With a few intermediate steps, this landmark paper in 2017, the Transformer, which dropped that assumption, moved to this model of reading an entire paragraph or an entire document kind of all at once in this sort of holistic parallel way, where the model essentially just kind of does a very coarse first pass of kind of coming up with some representation of every word in a document, and then conditioning on everything it's just figured out, sort of does a second pass and a third pass and a fourth pass. And you'll do this 50 or 100 times, kind of incrementally updating your representation of every piece of a document until you hit some predefined stopping point. You sort of hit your 100-step limit, and then you take those representations and you use those to do whatever task you're doing. And this I think very much fits this weird history of the field, because it's thinking from an NLP perspective, it's kind of a bad idea. There are some kind of clean theoretical reasons you expect this to be limited to not really reliably be able to do the thing you want. Because there are sort of all these things you expect humans to be able to do by reading something incrementally, sort of processing it, taking more time on longer pieces of text that just a transformer can't do. But what was so important about the transformer is that it worked very well with GPUs. It was possible to implement this very quickly, very efficiently with the hardware we had access to. That meant that we could train much larger models, train them much longer, and what we lost out on in clever ideas and clever designs, we're able to really make up by just having the model do more and more of the work, having the learning process do more and more of the work.
So, Sam, you mentioned the model a few times. Let's define it. Like, what is a large language model in sort of bite-sized pieces? And where does the magic come from? I mean, just this morning, I gave it a prompt. I said, give me a story that starts with, if you give a mouse a cookie. And it gave me one. And I said, now give me an adult one. It says, oh, sorry, I don't do adult stuff. I said, no, I mean for grown-ups. And it did. And it's amazing, right? It gave me a completely different type of story than a kid's story, right? So it got the context. How the hell does this thing work, right? I mean, it's gotten everyone's imagination. Like, everyone out there is playing with GPT. What is it? Like, what makes it work?
Yeah, so I could try to come at this from a couple of different angles. So first, I'll talk mechanistically about what it's trained to do, what the building blocks are, and then maybe come back and think a bit about sort of why it's turned out to be so impressive, why it's turned out to be able to do so much. Mechanistically, it's models like GPT-3, the kind of building block behind ChatGPT, these large language models, are autocomplete engines. They're fundamentally set up to do the same thing that your phone keyboard does when it suggests the next word. That what they're set up to do is look at some sort of left side context, look at kind of what has been written in a piece of text up to a certain stopping point, and predicting what word is going to come next. And sort of the way that you train these models, the way that these models develop most of their skills is you download a huge swath of the internet, sort of hundreds of billions or more words of text from everywhere you can find it, and just sort of try to teach this model to do autocomplete. we'll get to why this turns out to be so impressive. But so what's the model? What's the thing doing the autocomplete? It's a transformer neural network. And so that I think factors into two pieces. The code, the sort of actual computer program that implements this is pretty simple. Um, a smaller language model can be implemented in only a couple hundred lines of code. These things are really quite simple. Large language models take more, but only because just the hardware behind them is more complex. The sort of more efficiency tricks you need. But all it is this idea of you take a sequence of words and you apply sort of a handful of these linear algebraic transformations to, or so you take the sequence of words, you represent these as numbers. The sort of simplest way to think about them is just every word is a number between 0 and 50,000, representing just its place in the vocabulary. Um, you you sort of take these sequence of numbers, you apply a handful of pretty simple linear algebraic operations to them over and over again, and this produces some number at the output, which you can read back out as another word, potentially a prediction for what word comes next. What makes it possible to do such an impressive thing from such simple code is that those linear algebraic operations have all of these sort of free parameters that you're defining this very flexible sort of underdetermined computation that takes place. And there are all of these values that are kind of start out to set randomly that determine the behavior of the neural network. And then you do this training process where you show the model enormous amounts of data that gradually, incrementally sort of sets all of those free parameters. So a neural network is a few hundred lines of code and sort of hundreds of gigabytes of just numbers that define exactly what this big matrix multiply, exactly what this big linear algebraic operation does behind the scenes. And yes, the idea of the transformer was to kind of do a maximally simple, maximally general version of this, that we've just defined this piece of code that can do pretty arbitrary, pretty flexible computations. And what we sort of discovered, the discovery of large language models, is that if you take a sort of flexible enough neural network and a demanding enough task, and you put them together and you sort of run things for a long time, you get very, very subtle, intricate, complex behavior emerging at the other end. So I think what's kind of special about this autocomplete task is that it's sort of hard in just the right ways. That kind of you can use this autocomplete task to learn about parts of speech. You can use this autocomplete task to learn, kind of after a determiner like the, you probably get a noun coming next, or maybe an adjective. After sort of the word a, you get some nouns, and after the word an, you get some different nouns. That you can learn these very basic patterns about language. But also kind of once you've gotten there, the next thing that you learn that let you predict a little bit more accurately is maybe some sort of commonly stated facts about the world or some common phrases. You learn, sort of this idiom goes like this commonly repeated phrase goes like this. You learn common associations. You said, I was visiting San Francisco, and so I had a cold, windy, long walk across the Golden Gate blank, and you'll know, okay, bridge. And you keep training, you keep trying to figure out, all right, I've got that, I've memorized all of these common facts, and the model starts to kind of abstract more and more and learn more and more kind of high-level representations of, all right, what kinds of things do people talk about? How do they talk about them? How do they represent them? And eventually you wind up with something like ChatGPT, where you have a model that is at least apparently able to carry on a sort of coherent conversation almost entirely through this kind of autocomplete training process.
So that sounds pretty amazing, right? That it's designed to do this one really simple thing that it does well because it's trained on a lot of data. It learns patterns of language. It implicitly learns the rules of language. It implicitly learns relationships among things. But I guess, what really baffles people is and if I may be a little, I guess, use the word creative, right? That it seems to exhibit some sort of creativity. So, I mentioned the if you give a mouse a cookie story, and it went through that a few times, and I said, okay, now come up with a nice ending to the story, and it said, sure, right? And it came up with this one. I'll read it out. It said, as the date came to a close, the mouse was grateful for all the treats and adventures he had. He was surrounded by his favorite things, from cookies and milk to his soft bed and toys. But what he was most grateful for was the kindness of his friend who had given everything he wanted. And as he drifted off to sleep, he realized that sometimes the best things in life are the simple things: a cookie, a glass of milk, and a friend to share it with. Like, that is amazing, that it got all of that from my simple prompt that said, make that mouse the mouse story a little more for grown-ups. I mean, how was it able to do that behind the scenes? Like, where's the magic?
Yeah. So I almost want to say your guess is as good as mine. Um, yeah, we're in this strange position as a field where we built these small language models to do tasks like autocomplete. They also have been useful in translation and speech recognition, kind of filling in some gaps behind the scenes. And just kind of stumbled into the fact that as you make them bigger, they just become qualitatively more and more impressive. I think it's fair to say more and more creative, more and more flexible. And there's not, we're not really doing anything that differently. There's no idea from the engineering community that really made all of that possible. It's really kind of what the model itself is discovering in the data. And a lot of the kind of discussion in the field right now is sort of trying to figure out how to think about these things. Partially that's on, partially that's asking this very literal question of sort of why does this work? What is it doing? There's a lot of interest in looking at these neural networks after they've been trained, looking at all of these parameters, all of these linear algebraic operations, and trying to kind of reverse engineer what happened. But that's a very hard problem. That's analogous in many ways to doing neuroscience in humans, which is tremendously hard and something we're not that great at. So I don't think we can claim to have really understood what's happening inside the network just by looking at them. And there's also, I think, a big argument in the field about just kind of what level of description is right for these. How should we be thinking about these? Where, yeah, it gets fairly philosophical. There was a paper I really liked from Jacob Andreas at MIT that sort of took this interesting lens on what models are doing that I largely agree with. That's saying that kind of once these models get capable enough, they're what he calls agent models. That sort of when a language model is trying to predict the next word, if it's kind of all right, it's figured out the grammar, it's figured out the common associations, it's figured out kind of what text in general looks like. The next thing it's going to try to do is figure out sort of who is speaking and what they're like if it's predicting the next word in some piece of text. So if it's read a few paragraphs of a story on a fan fiction website, or it's read a few paragraphs of a blog or something like this, it's going to try to figure out, all right, sort of who's talking, what are they like, what's their background, what do they believe, how do they use language, and use that kind of reasoning as part of predicting the next word. So the consequence of that being that if you take a model and kind of prompt it with a context, a prompt that's kind of rich enough to evoke some kind of character, some kind of persona that it might have seen on the internet, it can kind of adopt that persona, adopt that character, and riff on that. But this is all pretty speculative. This is all, I think, just trying to reason from first principles about what these models are trained to do and what behavior we're actually seeing.
So this seems to be like, not surprisingly, this being academia, that some people feel like these are impressive and other people feel like they don't really understand anything, right? And these are like two extreme views. And I guess my question is a slightly different one, which is, are the foundations here strong enough and general enough for us to hope that this development is on the path to sort of general intelligence? Or is this something that we'll sort of look back and just sort of throw away and say, well, it was an interesting idea. It was a really impressive toy. It worked well for a while. It helped people improve their writing style, maybe, but that's kind of where it topped out, right? So I guess my question is like, are these foundations where you want to predict the next word and do autocomplete strong enough to actually build, systems that understand and form the basis for sort of more general purpose intelligence?
Yeah, this is the big question. I think we don't know the answer with much confidence, but I think this is really driving what a lot of us in the field are trying to figure out. The field is arguably splitting a bit based on people's views on this question. But yeah, we've got evidence pointing in a few different directions. So first, there's this kind of obvious bare fact that we've been talking about, that you take these systems that were doing things like phone autocomplete, that were doing these pretty unimpressive tasks sort of adequately well, and you just scale them up. You just give them more data and more money for more computer time, and you get all of these new abilities that many of which we didn't expect. So it just seems like qualitatively these things are getting better quite quickly, with no kind of obvious reason to believe that it would slow down, just from what we're observing externally. Um, there's also this kind of slightly more formalized version of roughly the same observation that gets called scaling laws, um, that points out that sort of one of the key measures of the capability of language models, not really their usefulness, but in some sense just kind of like one of these measures of how well they've understood the training data, which we think is related to how good they are at doing things we care about, that this gets better with scale really, really predictably. That if you look at very, very small language models, the kinds of things we could have built 5 years ago, and tried to extrapolate from then how good our models would be now, you'd be almost exactly right. So there's been a very, very clear systematic pattern in kind of how much better they get when you make them so and so much bigger or give them so and so much more data. So, and those extrapolations, those curves, don't show a kind of slowing down immediately in the horizon. There's arguments about how far out you can extrapolate this, but it seems like there's kind of pretty clear reason to believe that if we made something like GPT-3 100 times, 1,000 times bigger, gave it 100 or 1,000 times more data, that it would learn a lot more. What exactly it would do with that is a trickier question, but like we're pretty sure it would learn a lot more. So those are sort of two reasons to expect this trend can keep going. I think qualitatively also a lot of people in the field believe, and I think I largely agree, that autocomplete with enough data is probably enough to kind of teach you almost anything you might want to learn about the world. Eventually, you'll need to do something clever to get sort of visual grounding, spatial grounding, to get the model to like interact with the world beyond just text. But that really trying to sort of predict what people do, what people say, teaches you an enormous amount. And if you do enough of that, it's really hard to think of some sort of cognitive or language-related ability you can't learn that way. There are a couple places to look for limitations, for reasons things might slow down. And I don't see really knockdown reasons we should expect this to stop here, but there's reasons to be a little bit less optimistic. One of these is just the amount of data we have. These models are using a pretty big swath of everything that's on the internet. And at some point, we just run out of text to do autocomplete training on. And this, people argue about how soon this happens, but this could be within the next couple of years. And at that point, just kind of scaling these things up becomes much more expensive because you lost out on the kind of best, easiest, cheapest way of training these systems that we had access to, and you'll have to find something else. Another way that things could slow down is that there are some sort of deep limitations to the transformer design that seem probably fixable. Seems like there are probably ideas on the horizon that will patch these, but that are real limitations now. Um, One of these is that it's very expensive to make these models read really long text all at once. And so these models generally read at most a few pages of text at a time, and they can't really keep track of anything that falls outside of that context. So, for example, these models are sort of inevitably going to really struggle to learn a kind of deep intuition about the arc of an entire novel or an entire long story or an entire kind of news arc over many news articles. Um, because all it's ever learning are kind of associations within 4,000 word sort of passage. And it just turns out to be very expensive, very difficult to push models beyond that. Um, Another limitation is that models, these models sort of do a fixed amount of sort of thinking or processing for every word they produce. And this seems like kind of a more and more important limitation on kind of the hardest things that a model can do. So, for example, you might ask a model, um, sort of, what's the capital of Italy? Question mark. Doesn't have to think very hard. That's for a model like this. That's a really easy question. It just knows, oh, okay, I know this one. I've seen it before. Rome. No complex reasoning involved. You might also ask a model something like, what are the prime factors of this 12-digit number? And give it a 12-digit number. And then it's going to say, okay, the answer is. And it's got to do an enormous amount of really expensive computation and reasoning to figure out what to say next there. But the way that currently these models are designed, it actually does the same amount of work for both of these. So either you build a model that is powerful enough to do the math, but wildly overkill for things like telling you that Rome is the capital of Italy, and wildly too slow, wildly too expensive, or you build a model that is fast and efficient and can do the kind of everyday cases well, but that doesn't really have the capacity to sort of reason in depth about these hardest cases. This is another kind of technical challenge. We haven't figured out how to really cleanly, reliably separate kind of the easy cases where you can think quickly, kind of what you might hear called sort of system one reasoning in cognitive science, and the harder cases, the system two cases, where a model might ideally want to kind of stop and think about something.
That's really interesting, this contrast of the machine expending uniform effort on everything versus the fast and slow thinking that humans do, as described by Kahneman. Very interesting. So let's turn to a different side of these models that makes people nervous, and that's their potential to do serious harm. What are these potential harms, and how do we exercise oversight over systems to prevent them? Should we be concerned at all?
Yeah, I think there's reason to be pretty concerned. We're working with something that seems quite powerful that we, even as the people building this stuff, don't understand very well. I see kind of three categories of concerns that might be useful to factor this into, from kind of the most concrete, the most well demonstrated, to fairly speculative far out. So there's sort of concerns about what these systems are doing now, ways in which they're doing harm now, in this kind of moment before this stuff has really been widely deployed. That ChatGPT is this impressive tool. It's maybe starting to get used to cheat on essays, but I don't think it's really kind of landed in the economy in that deep a way yet. So right now, I think a lot of these concerns are about things like kind of cases here and there where systems like this might be used in resume screening and might be discriminatory in hiring, might reinforce kind of human discrimination, or relatedly ways in which these systems just kind of, when they're used casually, when they're used for things like sort of chat or autocomplete, they kind of bake in stereotypes. They'll talk in one way about one kind of person, another way about another kind of person, in a way that we wouldn't really endorse. These kind of stereotype-based harms, and also these kind of also you'll see some present-day concerns about things like concentration of power, where this is putting sort of a lot of money, a lot of influence, and the power of tech companies that aren't sort of, we don't really know how to regulate, don't have that huge of a staff. Um, so yeah, the sort of there are things that are happening now that are eventually quite worrying that are worth talking about. Yeah, so I think there's kind of, and then looking further out, you can kind of separate future concerns into, I think, two buckets. One of them is, I think, the the harms that we might be able to foresee from just kind of seeing the technology that's already here or very much on the horizon really fleshed out and realized and kind of integrated into the world. Um, and this is a little hard to reason about, but we kind of know, at least we know the basics. We know what something like ChatGPT can do. We can make pretty educated guesses uh, about if you tried to use it to automate away customer service workers, or if you tried to use it to do some kind of political manipulation, just like what it would be good at and what it wouldn't be. And I think there are, yeah, the effects of that are seem fairly big, fairly speculative, fairly hard to reason about. There's kind of talk of, at least in a small way, kind of like another industrial revolution or another internet revolution, just from deploying the kind of thing we have now. And that's going to be massively disruptive in probably a mix of good and potentially very bad ways. I think a lot of the concerns there are sort of societal, sort of about how we use this, how we regulate it, who uses it for what. Um, but on the technical side, you mentioned oversight. I think it's relevant that we don't really have great tools yet for telling these systems exactly what we want them to do and having them do exactly that. This is thing people have had a lot of fun with on the internet with ChatGPT. It seems like the sort of creators of the system at OpenAI put sort of a little bit of research, a little bit of work into making the systems sort of stay within some guide rails to say sort of not say slurs, not give people advice on how to do clearly unethical or harmful things, and sort of stay within this persona of kind of like a helpful AI assistant. And as many people on the internet have noticed, those guardrails aren't very strong. It's pretty easy to sort of come up with a way of sort of tricking the model into doing all of these things that this creators probably didn't want it to do. Um, and so I think that'll color a lot of these short-term deployment concerns that it's going to be hard to build a product that just straightforwardly, reliably sort of does thing X, that just reliably like handles Walmart returns or something like that, product returns. Because these systems are such these sort of powerful, generally capable systems that we've got only a limited ability to steer. The sort of third category of concerns, looking furthest out, are the sort of concerns that show up when you imagine these systems actually getting meaningfully better. When you imagine, all right, what happens if we make something like ChatGPT about 100 times or 1,000 times bigger? And I think you get an amplified version of all of these present day and near future concerns. You also get this new category that I think kind of the AI safety community is quite interested in, which are concerns that come from thinking of these systems more like kind of agents with goals that are acting in the world. And I think there's this expectation that these systems probably will eventually get pretty good at things like theory of mind, pretty good at figuring out kind of, oh, right now I'm a language model running in a data center, talking to this person, trying to talk them through this process of handling a Walmart return. And once a system has that level of understanding, it's able to sort of take coordinated actions, pursue long-term goals in a way that currently we don't really think is possible. And so there you have a system where if it decides for some reason, kind of, oh, sort of, I would do my job better if I had more compute. I would do my job better if this manager at the company that owns me were replaced by that manager, that you might have systems actually start to sort of subtly take actions to pursue these goals and be kind of wily and strategic and more resourced enough to start to kind of act in the world in ways that we wouldn't necessarily endorse or fully understand. And that opens up just kind of a whole crazy range of science fiction outcomes if we get to that point.
So, by the way,
Yeah.
if I may interrupt there, is that similar to what Stuart Russell and Brian Christian talk about in the alignment problem? That this process of sort of singularly optimizing an objective function can sometimes lead to side effects that we don't envision. For example, the machine saying, "Oh, if I could only eliminate that manager, I'd be able to do my goal better," and that's the goal, or it was a goal that we'd specified for it, that it sort of uh, as part of which it made up the sub goal of like, let me eliminate that manager and I'll be able to do my job better. So is this similar to sort of this alignment problem that they talk about?
Yeah, exactly. That's exactly right. I think I like this concept of alignment here. I think it helps think about this range of issues. So I think what alignment means in its most generic form is just taking a system that already has some knowledge, has some skills. This kind of base GPT-3 model has learned a lot about the world, has learned a lot about how to write. Alignment is the problem of taking that system and making it do the thing that you want, sort of giving it a goal and having it pursue that goal. And it can be hard. All of the sort of silly failure demos that you see on Twitter with ChatGPT are sort of classic examples of an alignment failure. They tried, at least a kind of rough first pass attempt, to make it this like helpful, polite assistant, and people are getting it to say horrible things if they try. So it was not that well aligned to that goal of being helpful and polite. You can also see even kind of these very simple bias-related issues as being alignment problems. That if you're building your customer service bot, resume screening bot, you want it to be fair and unbiased. It turns out that's hard. It turns out that you might easily miss some of the subtleties in the problem and release a system that actually does bake in all kinds of biases that get you in ethical and legal trouble. But yeah, I think when people talk about alignment, they're often pointing toward this particular reason that it's hard, that Stuart Russell has done a lot to popularize, that Brian Christian's book talks a lot about. Strongly recommend Brian Christian's book on this, The Alignment Problem, but which is this idea that kind of once you have a system that's pursuing long-term goals, it's likely to develop sub-goals. It's likely to develop sort of things that it wants to do in order to pursue its main goals. And those are really difficult to control, and those can sort of very easily go off the rails. That even if your main goal, the main thing you're trying to teach a system to do, is to be a polite AI assistant, even if it completely understands your goal and is completely trying to pursue it, it might say, hey, if I took over this data, if I hacked this other data center and took it over, I'd be able to do more processing, and so I'd be a better AI assistant. And so I'm going to go do that. And really unequivocally preventing that kind of thing, or sort of telling models to not try that kind of thing, is actually pretty hard and subtle. And there's even this additional subtlety, which is getting the models to learn the goal right in the first place is also tricky. So we've got problems where models don't quite learn the goals that we try to give them, and even if they do learn the goals we try to give them, don't quite reason in human-like ways or take kind of only human-like steps in figuring out how to pursue those goals. And a lot of this is fairly speculative. A lot of this is stuff where kind of our systems aren't strategic enough for these problems to arise. But I think the arguments for why they could arise are pretty sound and are, I think, a plausible thing to be thinking about when we talk about where these systems might be in 5 or 10 years.
So how should we think about oversight of AI systems that may become more capable than we are in many ways, so that they align more closely with human goals and don't go off the rails? You wrote a really interesting article on scalable oversight based on experiments that offers some hope that humans may be able to help AI to not go off the rails. Explain that thinking.
Yeah. So let me first set up a bit of what oversight and scalable oversight are and how these fit into the picture. The paper itself was kind of just a little playing around in trying to get a handle on this bigger problem. So oversight is just this kind of idea of teaching the model what to do in this very kind of external way, maybe kind of analogously to how we teach or incentivize a human, either teaching a kid or kind of showing an employee what we want them to do. This includes things like showing the model examples of what we want, or kind of rewarding and penalizing it for showing certain behaviors. And oversight isn't the only tool we have for alignment. Oversight is maybe contrasted with mechanisms that sort of directly mess with the internals of a model. But I think it's where it's the main lever we have. It's the main tool we have. It's where most of the progress we've been able to make on building things like ChatGPT have come from. So sort of oversight is teaching models what we want them to do. And scalable oversight is this sort of ambitious special case of that. So what scalable here means is that we assume that the model is in some important ways kind of more capable, more knowledgeable than we are, but we still have to supervise it. We still have to teach it. And this is a situation I think we already sometimes wind up in, that we'll have a model like GPT-3, this kind of base language model, and it has much more knowledge than any one individual person. It's memorized or synthesized kind of almost the entire internet, many books. But we're still the ones in charge. We still are the ones who know what we want, and we need to demonstrate that. And so scale oversight is this problem of kind of how do you teach a system to do what you want when it's better than you are at demonstrating what you want. It's better than you are at understanding what it is that you want. And maybe even kind of, you're not even fully qualified to sort of get into some of the details about what it is that you want. This may be a confusing way to explain it. This might be easier with a toy example that's kind of central to a lot of the work that we've been doing. Actually, this is a confusing enough mess. It might make sense to scratch this part.
Yeah, I mean, I think you talk about a healthcare situation, right? Where you've got healthcare experts who are clearly sort of, experts, but then the system has been trained on all kinds of stuff, I guess, including wrong things and hearsay and all of that stuff. So it has deep knowledge, but it might also have picked up some things that aren't appropriate.
Yeah. All right. So I can try to pick up there, and that's where I was hoping to wind up. So yeah, one example of what scalable oversight can look like in the real world, and one that I think previews ways in which we expect it to be harder and more important in the future, is this example from researcher Ajay Katra of trying to teach GPT-3 or ChatGPT to give medical advice. So the situation that we kind of assume that we're in this style of experiment is we've got a model like GPT-3, like ChatGPT, that's memorized or synthesized big swaths of the internet, including most of the medical literature. It's memorized most of the abstracts on PubMed. It sort of knows everything on WebMD. It's read up to date. It's read tons of forums for doctors. It just has a ton of medical knowledge. But it's also not necessarily out of the box doing what you want. It's also memorized tons of kind of junky Reddit discussions about medicine and health, and it's memorized lots of pseudoscience. And if you just kind of straightforwardly prompt it with kind of, hey, sort of tell me what I should do about this strange headache that's shown up, you're not necessarily going to want to trust it. You're not necessarily going to know, is its answer coming from sort of the best and most recent medical knowledge and insight, or is it coming from some conspiracy theory that's floating around mailing lists in 1996? And I'm sort of interested in this task of how you teach a model to do this without hiring a bunch of doctors to play a role in the process. And this is the reason I'm sort of leaving out the doctors is for a couple of reasons. I'm interested in doing this first for practical reasons, that these systems should be able to help us do this oversight, should be able to help us figure out how to teach them, help us figure out sort of what medical knowledge to use. Like this should be kind of a lot easier and more efficient if we take the system that already knows everything we want and just kind of converse with it, interact with it in a way that draws out that knowledge. So practically it'd be useful to do this without bringing in experts in every possible domain of expertise every time we want to teach a model something or ask a model to do something. There's also this kind of subtler, longer term aspiration that eventually these models will start to understand things that sort of really no human understands. That we expect them to start to synthesize knowledge where you only really start to notice something if, say, you have a PhD in epidemiology and a PhD in physics and a PhD in literature and an MD, and you start to notice this connection, and there's some interesting observation you can make. And if we're trying to get a model to talk to us about something that requires that observation, there is no person we can ask who can supervise that task. This gets a little speculative. It's unclear exactly what this would look like, but I think we should assume that as systems get better, more and more often they'll be relying on knowledge, relying on insights that doesn't really map on to something any one human can do. So we're interested in this research task of basically, how do you get a system like GPT-3 to do something like give you medical advice when you can't call a doctor, you can't look things up on UpToDate, the sort of medical advice website, to help you. And so what you're sort of stuck with at this point is finding ways of interacting with the model, finding ways of incentivizing the model that encourage it to sort of tell you how it's thinking, tell you all of its considerations, tell you why it thinks it knows what it knows, and to use all of that to then give oversight, to then say, oh, okay, do this, not that. Oh, okay, that first answer was good, that second answer was bad.
I guess in a sense, that's also sort of tweaking the system to sort of align it more with what you're looking for, isn't it?
Yeah, exactly. This is very much kind of a big subproblem of alignment of how do we incentivize systems, how do we reward systems, how do we show systems what we want when they're in some sense more capable than we are.
By the way, there was another thing I picked up when I sort of dug deeper into sort of the experiments that you ran, and that is that in one of the experiments anyway, you gave people answering under time pressure because they couldn't process the whole thing and they had to respond within a certain amount of time. And so the question was, could they use the language model effectively to sort of give them the right information to come up with the right answer? I don't know if that came out correctly.
Yeah, completely.
Yeah, but I thought that was fascinating, right? Because when I was thinking of like use cases of these language models, I would think that there are times when you're just under time pressure. You know, you've got to produce something or you've got to come up with an answer within a certain amount of time, and you don't have the time or the energy to sort of go scour the internet. You've got this sort of ready-made resource, and you use it to query and sort of come up with answers to questions relatively quickly, right? That seems like a potentially compelling kind of use case.
Yeah. I think there are a couple angles, a couple directions I can go here. First, yeah, I think this issue of time is super important in thinking about what these systems can do. That I think they read faster than humans. They don't get tired. They can read kind of more all at once. They're reading thousands of words kind of in parallel. And even when these systems aren't kind of more knowledgeable or sort of better at some task than humans are, they can still have this huge impact by just being faster. Both in I think kind of very straightforward, obvious ways, like, I don't know, if you're following the financial news and want to sell some security as soon as you see something mentioned in the news, then this lets you get a reasonably nuanced understanding of a news article a lot faster than having a human actually read it. I think some of the precursor technologies, GB3, have been used for this kind of thing in the past. And also, I think kind of subtler, slower, big picture things where just like you want to do a literature review on the topic and you've got a week to do it, but there's far more literature on that topic than you can read in a week, and a model like ChatGPT might miss some things, might not be quite as good at some of the nuance, but it can read 1,000 times more than you can in a week, and that gives it the certain kind of power. I think this is true both now and looking forward into the future. That if you imagine, I don't know, if you imagine a system that's merely as good as kind of the average person at sort of reasoning about politics and getting into political arguments, that's still a very scary prospect for misinformation, because you can have a system that sort of gets into political arguments on social media 100 at a time every second of every day without sleeping, and that opens up much weirder outcomes than we get from sort of farming now. So yeah, I think time is this interesting angle in general. The way we're using it in this experiment is related to that, but I think a little bit less exciting. What I was doing in this paper with collaborators at Anthropic, this lab I'm doing a sabbatical at, is just trying to kind of lay some groundwork to do more ambitious experimental research on scalable oversight. So there have been a lot of kind of theoretical arguments about how to do scalable oversight, about how to sort of use models to oversee models, use models to help us oversee models. The experiments have been pretty messy because we haven't had great proxy tasks to sort of show us what success looks like. And so this paper was setting up a few proxy tasks. One of them was kind of analogous to the medical reasoning question, was getting sort of lay people to answer graduate and professional exam questions without consulting the internet. So I might give you a question from the MCAT or a question from an accounting licensing exam or something like this, and you just have to work with the model to get it to help you answer. That's close to what I was talking about earlier. The other thing we sketch out in this paper as a potentially interesting direction is around reading long texts, where the task that we give people there is they have to sort of work with the model to really reliably, really confidently answer reading comprehension questions about these sort of long short stories, these like New Yorker magazine length short stories, the kind of thing that might take 45 minutes to read. These are reading comprehension questions that we put together that we think are both subtle and that are subtle, that require understanding the whole text. And the humans have only 10 minutes to do it. And the model can read this whole thing in half a second. So the model has this huge advantage over the human that it's read the whole story, whereas the human just can't get through the whole story. They can skim, they can search, they can read a few passages, but they are going to have to find some way of relying on the model's understanding, at least some of the time, if they're going to be able to reliably answer these questions. And we mostly just kind of threw this out there as an open problem. The basic thing we tried is just giving our human annotators access to a model a lot like ChatGPT, where they just are chatting with the model, asking it questions, cross-examining it, probing why it says what it says, and hopefully by the end of 10 minutes coming up with an answer. But I think we're really aiming for this to be a test bed for more complex, more subtle interventions where we're playing more with the model's incentives, we're looking more at why a model knows what it knows, and trying to get kind of more reliable, more confident answers that way.
Very, very cool. Say a little bit more about the results that you got from this experiment.
Yeah, so the results were kind of we're nice, but like we made progress on the problem, but we definitely didn't solve it. So what we found is for both of these categories of problems, for these reading comprehension questions that my lab put together here at NYU, and for these professional exam questions that a group at Berkeley compiled, that human participants who used the model were significantly more accurate than people under the same constraints who didn't have access to the model. So if you just give sort of a smart person we hire over the internet a medical exam question, they can make an educated guess. They'll do better than completely random, but they'll basically do pretty badly. If you give them access to a model like ChatGPT, in this case the Anthropic model, which is quite similar, they'll be able to learn a lot pretty quickly and answer pretty accurately. So they'll go from, depending on what you're measuring, maybe 50% accuracy to 70% accuracy on a multiple choice question. We also noticed, and this is not in the version of the paper that's out yet, but we should have a follow-up soon, this clearly gets better as the models get better. If we sort of make a slightly improved version of the model that's sort of trained on more text, the people working with it will answer questions more accurately. But the problem is still very much open. The sort of people we're working with these questions are still hard. They're still answering them with sort of less than 80% accuracy. The problem's very much unsolved. And the humans aren't confident that they mark whenever they answer each question, sort of how sure they are of the answer. They're very often still guessing. And for the kind of long-term goal that we're aiming at here, the long-term problem we want to solve, we really want it to be the case that sort of the people in the role of the human here are able to really answer questions in full confidence, in full knowledge of why the answer is what it is, rather than just kind of making educated guesses. I think that's how we really get oversight to work. That's how we really make progress on alignment.
Yeah, that's very cool. And I was thinking of the larger implications of this, which is that and I mean, maybe it's a bit of a stretch, but I mean, what the results suggest to me is that these kinds of models should actually enable people to learn better, especially under time constraints, right? You don't have forever to do your homework and learn stuff. I mean, maybe this will sort of speed up learning and make people better.
Yeah, I think that's right. Yeah, I think generally a lot of my interest lately has been on safety concerns and sort of medium long term risk from these technologies. But I should also say I find them incredibly exciting. I think there's a huge amount you could do that would be valuable here, and I think just making really excellent sort of top university quality tutoring available to pretty much everyone is sort of high on that list of reasons I'm excited about how this technology is going to play out in the next couple of years.
Yeah, yeah. So, Sam, to wind up this conversation, I want to come back to something we talked about a little bit earlier, which is the importance of sort of guardrails and rules potentially. Right? So, one of the things that happened in 1996, with Section 230 of the Telecommunications Act, is we just sort of didn't really think about the implications of the internet and search and the fact that there was going to be all of this data generated, and this data was going to have tremendous value to companies that were collecting it, right? Like Google and Facebook and just sort of the big Web 2.0 companies. Is that something we should be thinking about carefully now, given that we now have this technology that's even more powerful than search? We have the ability to, for people to create content, do all kinds of new things with this powerful technology. Are there some guardrails that we should be thinking about, or that regulators should be thinking about? And I know this is really hard to do because, it was impossible in the late 90s to envision how the internet would turn out. But, maybe we should have thought about an appeals process or just things like that around content. Is there something we should be thinking about here that we might kick ourselves, 20 years down the road and said, should have been a little more thoughtful about that?
Yeah, absolutely. This is such a hard problem. I think if this is the problem in the world where I if I could sort of snap my fingers and have the thousand most clever, most resourceful people get together and figure something out, it would be this problem is how do we kind of lay the groundwork for governance of this kind of technology? I think it's obviously important for exactly the reasons you gave, but it's hard in the same way that sort of coming up with something like Section 230 was hard, in that we really don't have a clear picture of how the technology is going to play out, sort of what harms, what responsibilities we're thinking about. I think it's hard in even subtler ways than that, because we've maybe even less of a roadmap of just what's possible, of like what kinds of things these systems will end up being able to do, and whether they'll be more like tools or more like agents acting in the world. Um, and also it's hard for a few other reasons. There's kind of a lively open source community building up around this stuff, in a way that maybe wasn't quite as possible with kind of the literal infrastructure of the internet, where things that kind of companies don't do or can't do are likely to, at least at some point, sort of happen anyway, in the open source domain. And also, I think there are big geopolitical concerns here that if a lot of the concerns around this technology have to do with things like political information and surveillance, there is a sort of genuine national security consideration that you don't want your country to overregulate technology, stop innovation, fall behind, because then that puts you at risk of being exploited by sort of other countries, other governments that are further ahead. So you both don't want to get too far ahead. You don't want to race ahead. You don't want to build technology that's going to mess up democracy, undermine civil society, by being deployed sloppily. You also don't want to overregulate it and wind up in a position where if someone else builds something sloppily, you get all of the cost and none of the benefits. So it's a really delicate problem, and I know there are smart people working on this. I don't think there are nearly enough.
Well, thanks for that, Sam. This is a question I'm sort of deeply interested in myself. So maybe it's time to think about organizing a workshop in this arena if one hasn't if one doesn't exist already. Any last minute thoughts, Sam, before we wind up? This has been a fascinating conversation. Thanks so much for your time. I have no idea where the hour went, or the hour and 15 minutes. Any concluding thoughts?
No, I think there's so much more to say on all of this. I think the biggest thing is just we're all a little bit in the dark here. That I think this technology has been a surprise, even to a lot of people who helped develop it. I'm sort of spending this year on sabbatical at Anthropic, which is a lab that was founded by many of the people on the GPT-3 team who built this stuff, and I can say nobody saw a lot of this recent progress coming. So yeah, it's a weird, scary, important moment in the technology, and really glad to get to talk it through with you. Thanks, Susan.
Yeah, thanks for that, Sam. Yeah, it has surprised a lot of people. I was out on the West Coast, and everyone who I talked to said, including people at Microsoft, said they were amazed and surprised at the rate of progress. So I think it's caught everyone by surprise. It's a great problem to have, isn't it? When something works better than you expect, it's a good problem to work with.
Yeah, great, and sometimes scary.
Indeed. Well, thanks so much, Sam. Look forward to more conversations on this subject. I'm sure, when we look at GPT-3 a year or two from now, we'll be probably as amazed as we are now. That would be my guess.
Likewise, and see you soon back in New York.
Yeah, cool. Thanks again, Sam. See you soon.